Today, we're pulling back the curtain on one of the most fundamental concepts in computer science, algorithms. Think of them as the secret recipes that power our entire digital world. Let's get started. So, how do computers actually solve problems? They don't think like we do. They can't just have a flash of insight. They need a precise step-by-step plan of action. And that plan is the heart of what we're going to uncover today. And what's fascinating is that this isn't just a mechanical process. As Professor Amos Fiat says, there's no magic formula. Every computational problem is a brand new creative challenge. This blend of pure logic and human creativity is what makes the field so compelling.
Okay, first things first, let's cut through the jargon. What is an algorithm, really?
It's a lot like cooking. Before you can write a recipe, you have to know exactly what dish you're making. Something tasty just isn't specific enough. In computing, it's the exact same idea. Before you can build a solution, you have to perfectly define the problem. And that leads us to our first key concept, the computational problem, which is the formal way we define the challenge. The crucial point here is that a computational problem simply describes the relationship between a given input and a desired output. Now notice, we're not talking about how to get there yet. We're only defining the what we start with and what we want to end up with. Let's make this tangible. We're going to use a simple example that'll stick with us through this whole explanation, the problem of summing up all the numbers in an array, which is basically just a list of numbers. For instance, if the input is an array with just the number 7, the output is 7. If the input is -3 and 2, the output is -1. For the array with 12, -4, 5, and 9, the desired output is 22. Simple, right? We've perfectly defined the what without a single word about the how. So we've defined our dish. Now it's time to write the recipe. This is where the algorithm comes in, the step-by-step method for solving the problem. And the formal definition here is critical. An algorithm is a sequence of unambiguous instructions that is also finite. That means every step is crystal clear and the process is guaranteed to end. It has to work for every valid input, it has to always stop, and it has to always return the correct output. Meet the hero of our explanation, the sum array algorithm. To describe algorithms clearly, we often use pseudocode, which is like a simplified, human-readable programming language. The logic is simple. You start with a sum that equals 0. Then, you go through every number in the list, one by one, and add it to the running total. When you've gone through all the numbers, that final sum is our answer. Let's do a quick dry run to see it in action with the array 5 to -1. We start our sum at 0. In the first loop, we add 5, so the sum becomes 5. In the second loop, we add 2, and the sum is 7. In the third loop, we add -1, and the sum becomes 6. The loop finishes, and the algorithm returns the correct answer, 6. It works. But hang on. Our recipe worked for this dish. But how do we know it'll work for every possible dish? This brings us to another critical stage, the test of reliability, or what's formally known as proof of correctness. This is the key question. A dry run is great, but there are an infinite number of possible arrays out there. You could have an array with 1,000,000 numbers or 1,000,000,000. How can we be absolutely sure our algorithm will work for every single one of them? The answer is, we can't. You can't test your way to absolute certainty when you're dealing with infinity. Instead, we need a formal, logical argument, a mathematical proof, that guarantees our algorithm is correct for any possible input. For algorithms with loops, a common method is using a loop invariant. Now, that sounds complicated, but the idea is actually pretty straightforward. It's a 4-step logical argument. First, you define a property that should always be true. Second, you prove it's true before the loop even starts. Third, and this is the clever part, you prove that if it's true on one iteration, it remains true for the next one. And finally, you show that this property, being preserved all the way to the end, guarantees that the algorithm's final answer is correct. For our sum array algorithm, the loop invariant is this. At the end of the ith iteration of the loop, the variable sum holds the exact sum of the first I elements of the array. If we can prove that this property is maintained from the start to the end of the loop, we have mathematically proven that the entire algorithm is correct. Okay, so our algorithm has been proven correct. It always gives the right answer. But there's one more vital question. Is it efficient? This is where we analyze its complexity. Correctness is non-negotiable. But a correct algorithm that takes 1,000,000,000 years to run isn't very useful. We need to analyze how its performance changes as the problem gets bigger. So, is it fast? We measure this with time complexity. This isn't about seconds or minutes because that depends on the computer. Instead, it's a function that describes how the number of steps an algorithm takes grows as the size of the input, which we call n, grows. Analyzing our sum array algorithm is pretty simple. If our input list has n numbers, our loop has to run exactly n times. The work done in each loop, a simple addition, is constant. Therefore, the total runtime grows in direct proportion to the size of the input. We call this linear time complexity. And this is the formal notation for that, theta of n. When you see this, it just means the algorithm's runtime is linear. Double the input size, and you roughly double the time it takes to run. It's a very predictable and generally efficient type of algorithm. So let's zoom out for a second and look at the whole journey. We've gone from a vague idea to a proven, efficient solution. This structured way of thinking is the very essence of computer science. Our journey started with an abstract challenge. We defined it precisely with inputs and outputs. We created the recipe, our algorithm. Then we proved that the recipe was reliable, and finally we measured its efficiency. This structured path from a fuzzy problem to a proven, efficient solution is more than just coding. It's a powerful way of thinking that builds our entire digital world. So the next time you use any app, take a moment to appreciate the elegant, hidden recipes running under the hood.